So good morning and welcome to the 6th lecture on module 3, which is on multi-level implementation. So in this in the third module of the design part of the lecture, what we have seen that given any binary function, so what you have to do, you have to try to represent it in terms of some minimized form. By minimized form means we have to represent it in minimum number of product terms and also each having minimum number of literal. So this would lead to what is the situation called implementation in terms of minimum number of gates. Then we have seen the exhaustive amount of algorithms, both heuristics and exact algorithms kind of stuff for two level Boolean function minimization. So whenever we mean by what do you mean by two level implementation means there will be AND gate, series of AND gates followed by OR gates, or if it is sum of product form, or if the product of some forms, then you have some of the AND gates followed by the OR gates. Okay, and so forth. I mean that means if you are having there is two ways of representing the functions, like sum of product form or product of some form, and generally you are using two levels to represent them. First may be the set of OR gates followed by a set of AND gates, so that is actually you have sum terms followed by product terms, or in the other way around you can have some AND gates, that is the product terms followed by some OR gates, which is the sum of those terms. So these are sum of product or product of some terms. Okay, but they are all in two level implementation. Then we have found out that although this two level implementation, the algorithm exists like that is Queen-McClellan's-Key, then you go for tabular method and then you go for branch and bound method, or if you want to go for heuristics you can go for espresso. So they can give you fairly well minimized functions, but also we have pointed out in those lectures that if you go for two level implementation there is some practical problem in the implementation view. So what it may happen is, if you have, say for example, if you have a function where there is one function, I mean there is a function say f, and one of the product terms may be say x1 dot 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 x30 and some plus is there. So this will actually involve something like a 30 input AND gate. So whether although this is possible in a two level implementation, it may be some kind of a minimized form. So but if you the idea that you require a 30 input AND gate is impractical in terms of implementation. So in terms of VLSI implementation, it is said that any gate having more than four fan outs is not desirable. So what do we require to do? So if you have a 30 level input AND gate, so you have to break it up into levels of 4. So there will be one 4 input AND gate, there will be another AND gate with 3 more inputs, and then be another this fourth and so forth. So you have to completely break it up into multiple levels. So what is the idea? That if you directly go for two level implementation, so some of the inputs for some of the gates may be as high as may very high, much more than 4. So it is found out that we'll tell you why. So it is found out that if you go for such type of implementation where the number of fan-ins of gates are more than 4, there is a lot of practical problem in implementation. The gate will be slower, and then it will lead to high power and so forth. So what do we go for is that we go for something called multi-level implementation. So in this case what happens? We first take a circuit or take a function, we minimize it in terms of two level fundamentals only, that is by you can use espresso if you are using heuristics, or branch and bound, whatever fits to you, but as you know that branch and bound is a highly time complex algorithm. So generally in the modern CAD tools espresso algorithm and its variants are used. So anyway you use some algorithm and then you minimize the minimize for two level implementation. Then what you do, you may find out that some of the gates may have a large number of inputs, so which is not practical to be implemented. Then we have to do what you have to do is that we have to break the two level implementation into multi-level implementation, and you have to keep it in mind such that none of the gates should have more than some amount of fan-ins. Like for example 4 is a very good thumb rule, that you should not have more than 4 input fan-in for any kind of gate, because that would lead to that gate becoming very slow in terms of speed, and also it may be high power consuming and so forth. So we will see. Okay, so let us take a sum of product form. This is a sum of product form. So in this case, if you see, this is already minimized sum of product form. You can take it from the words, because if you can find out that, you will find out that you cannot go for further minimization of this. So now if you want to implement this function in terms of this two level implementation, so it's a sum of product form, So in this case you have all these product terms here, and this is your sum term because it's odd. So you can find out the number or input of the OR gate is 1, 2, 3, 4 and 5. So this is a 5 input OR gate. Now what is the problem? So there is no problem, that you can implement this in a mathematical term. So this is minimized two level implementation, but the idea is that implementing this OR gate with 5 inputs is a big problem, because this would any gates in the more the number of fan-ins, the gate will be slow in operation and power consumption will be higher. So what we do is that we try to break it up into 2 OR gates maybe. So what you can do is to have a good implementation, you can put another OR gate over here, and this 5 you can put it over here, and this is the idea. So, I mean the now 1, 2, 3, 4 will be the number of fan-ins over here, the last fan-in you just put it over here, there is another OR gate. So, same function will be able to represent, but now it is level 1, 2 and it is 3 level implementation. So, we have to break it up into multiple levels. So, whenever the idea is that, so whenever I mean you have some fan gates with fan-ins more than 4, then you have to break it up into large number of levels, so that I mean the number of fan-ins of all the gates remains 4 or less. Now, let us see why does it happen. So, this is actually CMOS implementation of an OR gate. Okay. So, this is CMOS implementation of the 5 input OR gate 1, 2, 3, 4, 5. So, this is the OR gate. So, 5 inputs are there. So, this is CMOS implementation of the OR gate. So, there is an inverter, because I mean if you just we are not going to deal into details how the gate is designed, because this is some analog VLSI. So, you can find out in any standard VLSI design book that how an AND gate, NOR gate, NAND gate, how they are implemented in CMOS level. So, in CMOS you have to just see that these are your NMOS transistor and this is your PMOS. And this is an inverter, because generally we have is a NOR gate followed by inverter, which will make an OR gate. Okay, so now what you just see, so that in what happens. So, if it is a n input OR gate kind of a thing, or n input AND gate, whatever. So, in this chain you have n gates, n transistors, NMOS, and in this case you will have parallel n PMOS transistors. So, that is the idea. Now, you see this is okay, this is pretty okay. So, whenever the gate output is to be 1 or in other way. So, these PMOS transistors are used to charge, there is actually a capacitor over here. So, these things are used to charge your capacitor when you want the output of this point to be 1. So, in this inversion it will be 0, but that is what if you want when you want the value of here to be 0, that the input value at here to be 1. So, in this case what you have to do, you have these parallel transistors will charge this capacitor to be 1, so the answer will be 0. So, that is okay, because 5 parallel transistors are there, you may be using it for charging. But when you want the answer has to be 1 over here, then you have to get a value of 0 over here. So, in this case what happens, you have to discharge this capacitor through these transistors. Now, this is the NMOS transistors. Now, you see 1, 2, 3, 4, 5, more the number of fan-ins, more the number of NMOS transistor in chain will be there. So, if you have 30 input OR gate, so number of transistors here will be 30. And the time taken for discharge for this path will be very, very long. So, if you want an output transition from 0 to 1, the time taken will be very, very long, because you have to go on discharging through this series of NMOS transistors. So, it is a 5 input OR gate, so number of transistors in series is 5. So, that is why we try to limit it to 4, so that the discharge path does not become very long. And obviously, if you have more number of transistors, power requirement will be very high. So, if your N is very, very high, the fan in a gate is very, very high. So, the discharge path through the NMOS will be very, very high. So, the transition required is going to be very large, to make the operation of the gate slower. So, that is why we try to limit our input fan-ins to 4. Okay, that is what is the standard rule which is taken in VLSI design. Okay. So, whatever I told you is written in this slide. So, therefore, we require a multiple level implementation of this function. So, one very standard way of doing it is, you just very ad hoc way of doing it is, you just forget, do not add this 5 pin here in the OR gate, you just do it over here. Okay, but this is a very ad hoc kind of a rule of doing it, so that every level has the 3 level and every gate has 4 inputs. Okay, but in this lecture we will try to do it in a much more standard way, so that what we can say that factorization, that is the multiple level implementation is also in a very much minimized fashion. So, that means what? That is again the number of product terms or the number of cubes will be minimum, as well as the number of littles will also be minimum. So, that is how you have to do. So, in this case if I break it up into this OR gate, I break it up into 2. So, we will find out that we will see. In this case what we have done, so we have just taken another OR gate and we have just broken this up into this. So, it is a very ad hoc way of doing it. Now, what we will try to do? We will try to do it in a much more standard way. So, if you are doing it much more standard way, we will find out that the implementation will be much simpler or involving much less number of gates. So, that is what is the minimization here. Here the minimization will be, we have to make it in a multi-level format, that is the sum of product form, the product of some form you take, and then you implement in a multiple level. So, it will be factorized, okay, and also the factorization should be such that the implementation will be minimum number of gates, that is minimum number of terms, and also the number of literals in the term should be minimum, so that it will be minimum number of fan-ins for the gate. This same thing like your 2-level minimization, but here the levels will be much more in number. So, this is an ad hoc way of doing it, that you find out a gate which is having more than 5 inputs or the 4 inputs, then you break it up into 2 levels and you keep on doing it. It is a very ad hoc way of doing it, as we will very shortly see. So, for the same function, So, for the same function this one, okay, what we these people have done it in a different way. So, in this case this is the implementation. Same thing they have taken x1 x2, they have the common part, they have taken it out, x3 plus x4, x1 x5 and this one, and this will be implemented in this fashion. So, in this case you see how many gates are required, 1 2 3 4 5 6 gates are there, okay, and in this case also if you check, so is 1 2 3 4 5 6 gates are there. But one very important thing is, so this implementation is an ad hoc one which I have cut this OR gate and fed it here. So, in this case is 1 2 3 4 5 6 gates are there, and in this implementation also in this fashion, that is again you have broken up into multiple levels, but you have used the factorization over here. So, in this case you can see 1 2 3 4 5 6 gates are required, but the number of fan-ins of the gates you check, it is 2 here, it is 2 here, it is 2 here, 2 here, and it is 2 here, and it is 4 over here. But in this case if you check the number of fan inputs is 3 over here, 3 over here, in this case it is 4 over here. So, the number of fan-ins is, that is the fan-ins of the gates is higher in this case. So, that is why if you just take the ad hoc manner, that wherever you find out a gate with more than fan outs you break it, rather it will consume much more area over it, or the gates with more number of fan outs or terms, rather than if you go for this type of a factorized implementation where you have a much less number of fan-ins in the place. So, in this example both had 6 gates, but in a more practical situations you will find out the number of gates will also be lower in this case. Okay. So, in this expression what we have found out, that none of the gates have expression fan-ins more than 4, that was our desired thing. So, everywhere you have to keep it in mind. So, nowhere you should have a fan-in of more than 4 gates. So, if it is there, then you have to keep on factorizing it. Okay. Okay, then this factorized expression can also be further factorized into this. Okay, then this is you see, this is the beauty of this, is one level factorization. Then again you can find out that there is a common term over here. So, you can again factorize this in these terms leading to the circuit here. So, in this case you see 1 2 3 4 5 6 gates are also involved over there, but you can see that number of fan-ins have decreased much more over here. So, this is 2 2 2 2 1 2 2 2 2 1. Okay. So, in this case 1 2 3 4 5 6 7 8 9. So, 9 there were 9 literals in the input case. So, in this case 1 2 3 4 5 6 7 8. So, in this case you see 2 plus 2 4 5 6 7 8. So, there is actually 8 fan-ins in the input case, where it was, wherever it was actually 1 2 3 4 5 6 7 8 9. So, even by taking the common factor on this one and the factorization, so again you find out that the number of input fan-ins has become now 8. So, that is what I am saying, that if you keep on factorizing, then I mean there is going then the ad hoc way of doing it. If you keep on factorizing, you will find out that number of fan-ins in the inputs are decreasing, and also none of the gates have more than a certain number of fan-ins, like 4 in this, that is the thumb rule. But in more formal terms, what we are trying to achieve? We are trying to achieve a minimal representation of this function. This is your function. So, you are trying to represent it in a minimal multiple level format, and so when do you say it is a minimized representation? The minimized representation will be such so that it cannot be refactored again. So, none of the terms here can be factorized further. So, that means what? That is now it is factorized in the best way. So, it implies that there is the minimum number of literals and minimum number of, that is the minimum number of literals and minimum number of terms, implying minimum number of gates and minimum number of fan-ins. So, that is what in case of 2 level implementation we are also trying to do the same thing. We are trying to reduce the terms, and we are also trying to reduce the number of literals in there. But in this case, as it is a multi-level implementation, so we have to reduce the terms and also reduce the number of literals, and at the same time we are to do factorization, because we are going for multi-level implementation, and the factorization should be such that no more terms can be refactored again. That is the minimum number of, that is almost we have reached the bottom level, so that the number of we can achieve a minimal representation in terms of gates. Okay. So, that is the idea. So, this is actually the best way of factorized term for this one. So, this is the minimal representation, because no more terms can be factorized anymore. So, this is the minimal factorized form which is realized as a multi-level implementation. So, that is the target. So, we will be giving a sum of product form in this way, and you have to go for a maximum factorized form. That is what is the minimization in multi-level implementation. Okay. So, this was what we have discussed by what you say as a small example. Now, we will go to the formal algorithm, where we will try to show how can we do the factorization. Okay. So, that is a factorizing a sum of product form. This can also be done for a POS form, but mainly in this lecture we will be concentrating on the sum of product form. Okay. So, before going that, so let us go for some standard definitions and all, then we will go for the exact algorithm. Okay. So, an alternate representation of the SOP form of a logic function which is closer to physical multi-level implementation is a factored form. So, if it is a POS or a SOP form, so it is 2 level. So, if you are going for a factorized stuff, it is more level to a multi-level implementation. Okay. It is the generalization of SOP form which is allowing nested parentheses. For example, each of them following is a factor, right? 1 literal, 3 literals. This is also 1, 2, 3, 4, 2 cubes, you can say, and there are 4 literals. In this case, it is 1, 2, 3, 3 terms, and 1, 2. In this case, 1, 2, 3, 4 terms, 4 literals, and so forth. You can do this. Okay. So this one are the literals of the factored form. Factored forms are generally derived from SOP, minimized SOP form. That is why, I mean, if somebody asks you a question that if I have to do in a multi-level implementation, then why do you go for a 2-level implementation? The idea is that you cannot directly jump into multi-level implementation. 2-level implementation is still to the very date backbone of Boolean function minimization. So what do you do? First, you have given a SOP form, you have to go for a 2-level minimization, and from the 2-level minimization form, you can go for multi-level implementation. That is, you have to minimize, that is, given a Boolean function in any arbitrary way. So you have to first obtain the minimized SOP form, that is, you may minimize 2-level implemented form, and from the 2-level implementation minimized form, you can again factorize it to the maximal level, so that it becomes a minimized multiple level implementation format. So that is why 2-level implementation till date has a very great role in minimization of circuit implementation. Okay. So that is why factored forms are derived from minimized SOP forms. So minimized SOP forms can only be derived if you are going for a 2-level minimization algorithms. If you are using 2-level minimization algorithms, then only you can get minimized SOP forms. So the SOP expression, this one, okay, can be factored as this one. So this is another example they are saying. So x1, x3, x5, and this one. So you can break it up as x5, you can take as common. Between this x5 prime is alone. So this x5 is common everywhere. So you can take this. Then you can find that x1 plus x2 and x3 plus x4. If you can factor them in this way, you can get it. So basically what happens, so this can be easily represented in a factorized form in this one. So basically a factored form is sum of product of sum of product of sum of product dot dot dot. So you can see this is again sum of product form, like x1 plus x2 is sum of product form. In this case also you can see this is a sum of product form. Again, I mean, you can see that this is nothing but a sum of product form, and the whole thing is also, you can say, a sum of product form. If you can think this is one term, this is one term, and this is one term, then is actually nothing but sum of product form. You do not consider this stuff inside the bracket, you have just consider this one as one term, this one as one term, this one is one term, obviously these are single terms and these are single terms. So this plus this is a sum of product form. But now inside each of the element, again you can break it up into sum of product form, and this can be done in a nested way of arbitrary. That is what is a factored form. Okay. So now a factored form can be defined in the following way. A product is either a single literal or product of factored form, that is very obvious. A sum is either a single literal or a sum of factored forms. A factored form is either a product or a sum. So using these 3 rules, you can find out what is a factored form. So very example is, this is a single literal, is a factored form. This is again a single literal, is a factored form. This one is either a single literal or sum of product form. So in this case you can see it is a sum of factored forms. So in this case it is a sum of some factored form. So this is also a factored term, and again this is actually sum of product of sum of product of sum of product. So this is also nothing but a factored form. So this is what is the definition, that is recursively you can define a factored form in this way. So that is why I told you this is one product, this is one term, and this is one. So this is the product of 2 terms, and this is the third term. So you can say that this is a sum of product form. Okay. So this is a single literal, and this is say term 1, this is term 2, this is a product, and this is sum. So this is a sum of product form. Now inside this blocks again is again term 1, term 2, this is again product form. So this is again a sum of product form, and you keep on doing it. So where the first 2 literals, first 2 are literals, the third is a product, okay, the fourth is a sum, you can sum, and the last one is a sum of product of sum of product of sum of product. So these are nested definition as is given here. So these are nested definition of a factored SOP. So that is why you have to consider, when you are looking at the top level, so you have to consider this is term 1, this is term 2, and this is term 3. So sum of product form. Now again if you go inside term 1, it is again a sum of product form, but each of the term is a single literal here. Again if you go to again term 2, this is again a sum of product form. These two are single literals, and this guy is a product term. So this is how you can define the factored forms. So now which is not a factored form, that is also very important. So according to definition, this is not a factored form, because this you can open it up. This can be opened up as, because it is x1 plus x2 whole complement. So this you cannot represent something like this. This does not follow this definition. So this can be represented as a x1 bar dot x2 bar. By De Morgan's law you can find it out. Then this will become a factored form. Similarly this one also is not a factored form, because you can see that is x1 dot x2 whole bar. This will be nothing but x1 plus x2 this one plus this one, sorry. So, this one will be your something like De Morgan. So, just I mean you can open it up into your De Morgan's law. So, you can find it out, then this one will become your factored form. So, this is if you have some expression like this. So, this is not this SOP form, then this will not be your factored form. So, okay, because they are complementary internally, which is not allowed by the definition. Also, it might be noted that like 2-level SOP, factored forms in general are not unique as illustrated by the following equivalent form. So, we know that is for a single function there can be multiple way of implementation in 2 levels as I already seen. So, it's in the same way factored forms they are not unique, because you see these two are, you can find out their equivalent. So, this one is nothing but x1 x2, this one if you open it up, plus x3 x1 plus x3 x2. Now, if you just open it up, this one also you will find out that it is x2 x3 plus x1 x2 plus x1 x3. So, you can find out that these two are equivalent. So, in other words, so just like a 2-level implementation form, so SOP form or POS form, they are not unique for a given function. So, multiple level implementation is also not unique. Okay. Now, let us go to the next definition. So, it says that an algebraic expression, this is f of c1 plus c2, but these are nothing but the cubes, is 1. So, an algebraic expression is 1 where no cubes contain another, that is none of this cube is totally embedded in another, then it is an algebraic expression, and expression that is not algebraic is called Boolean. So, in case of Boolean, one may be included in the other. For example, this one is algebraic because this one is not in this, neither this one is in this term. Okay, and expression this one is non algebraic because this whole term you can see is inside this one. This is true. So, in this case, be not algebraic, this one is not algebraic and this one is algebraic because x1 is not in this one, and in this case, sorry, this is a, I mean it will be something like this you can say. So, this is the case, sorry. So, typo over here. So, this is not algebraic because S1 is not included in here, and this one is Boolean, that is non algebraic. So, first one is sorry, this expression is algebraic because x1 is not a part of this one, that in other words, so this term, this cube is not inside this, so that is why it is algebraic, and the expression this one is a non algebraic expression. Why? Because this whole C is in this one, implying that this one is the case. So, this one is subset equal to this is what is written, cut is should not be there, this is a typo from my side, sorry for that. Okay, and in this case this is not, does not belong to this one. So, x1 does not belong to this, this implies that C2 okay, is that is C1, sorry, C, that is this what does it mean? That means none of the literal from C1 is in C2 and vice versa. So, that means what? That is C1 is this will not hold by C2. That means what I mean over here is that as x1 is not as the literal is present in C1 is not in C1, C2 or x4, that will mean that C1 will not belong to C2 and so forth. Okay, and neither C2 will be a subset of this one. Okay, but now you can see in this case neither, now this is also true, this will also be true over this. Okay, because x1 is not in this form. Okay, I mean this does not, but x1 is, but if you see the two expression like the expression this one, okay, x1 plus x1 plus x3 x4, this one, in this case this is not algebraic, this is Boolean because this literal is a part of this one implies that if you consider it as C2 and if you compare C1, so in this case this will be the case, okay, that C2 will be inside C1. So, in this case it will remain a Boolean. Okay. So, now just another definition, a factored form f is said to be algebraic if the SOP expression obtained by multiplying f out directly, okay, that is we will see what does it mean, algebraic, and is Boolean if it is not algebraic. That is, if you are given a factored form something like this, now if you open it up, okay, if you multiply this, that is these things you should implement and these things should not be there, that is this type of minimizations you should eliminate, that is if you have x1 plus x1 make it 0 and eliminate, if you have x1 you keep it as x1, do not keep it as x1 and not x1, okay, and single cube containment, all those things, that is all these type of minimizations you should do, and if it becomes a algebraic expression, okay, then it will be an algebraic factored form, otherwise it will become a Boolean factored form. For example, each of the following is an algebraic factored form, right, because x1, x2, x3. So, even if I open it up, it is already opened, so x1 does not belong to x2 or x3. So, in this it becomes an algebraic format. Now, if you look at this one, this I can open it up. So, if you can open it up, it will be what? It will be x1, if you just open it up, I mean this is x1, x3 plus x1, x4, x5, and then if you open it x2, x3 plus you can have x2, x3, x2, x4, x5 plus x6. So, you can easily find out that none of the terms will be totally inside another, right. So, that is what is being saying, that algebra this is in which no cube contains another. Okay. So, in this case you can very easily find out that none of the cubes will contain each other. Okay. So, in this case this is obviously and we have there is no terms like this one, so that you need not think about it. Like for example, we do not, if we had something like this one, then we have to eliminate this term. Okay. So, as nothing is there, so you can easily say that these two are algebraic formatted, algebraic factored form, because none of the cube contains another. Okay. The following is the Boolean factored form, because obviously if you look at this, already we have told that this, if you consider this as C1, this you consider C2, so C1 will comprise C2. So, in this case this is not. Okay. Similarly, you can easily find out that in this case also, if you open it up, so you will find out that this is a non-algebraic factored form, because first way you will find out that x1 prime. So, this will actually kill you. So, you can easily find out, if you just go ahead, just open this expression. So, you can easily find out that this factored form, this will by looking at definition 2 and just opening it up, we will find out that this is a Boolean factored form and not an algebraic factored form. Okay. So, so now what we have seen is that in this section, so there can be multiple equivalent factored form. Okay. So, the difference in the number of literals can be significant. Okay. So, but what is the idea? Just like it is said that, as discussed in the introduction section, there can be many equivalent factored forms of a given SOP expression. Also, the difference in the number of literals of these equivalent forms can be significant. That is already given in this example. That is you can see that in this case the input is 8. We have an input fan, it is same thing if you do it in this way, input fan in is 9, and if you are not going for a factored form, then it can be very high, 3 plus 3 6, 7 8 9 10 11. So, that is for a same function there can be different factored forms and the number of inputs can be different. Okay. So, that is why we will also illustrate this using another example in the question answer session, and that is why we have to go for such a factored form where the number of input fan-ins are minimum, as well as the number of terms also should be minimum. So, that then only we can say that it is a maximally factored form, and that will require the minimum number of implementation. So, slowly we are going towards that. So, we are slowly going towards different definition. First we have seen what is the definition of a Boolean factored form and what is the algebraic factored form. First we have also seen what is the factored form, then we have seen what is the Boolean factored form and algebraic factored form, and slowly by using this we are we will find out algorithms which can give you what is the best or the maximally factored form which is the best for implementation. So, slowly we will go, but you have to keep in mind, just like a simple SOP sum of product 2-level implementation or a product of some 2-level implementation or minimization, there can be, say for the same function there can be different 2-level implementation. Similarly, for multi-level implementation also there can be different factored forms leading to different type of implementation for the same function. Okay. So, therefore, we require algorithms to be generated that can generate factored forms having minimal number of literals that will lead to minimal implementation, that minimal level implementation. So, that is efficient in terms of area. In other words, we need scheme for factored forms which are maximally factored for efficient multi-level circuit implementation. So, we require some algorithms which we will be studying now, which can, given a SOP, minimized SOP form, which can go for the maximum factored or maximally factored way. Maximally factored, they will take the minimized SOP form and then they will factorize it maximally, so that the number of literals and terms in them will be minimum, it will be very less or will be as minimum as possible, so that the implementation is area efficient. Okay. So, now let us take the definition of what do you mean by a maximally factored form. So, in other words, in layman's language, what is the maximally factored form? Given any sum of product, minimized sum of product form, it will be considered as maximally factored if none of the terms can be again factored. Okay. That is in one way of doing it. Okay. But that is a very layman way of saying it, that is once it is so much factored that no more terms can be refactored again. So, okay, but let us now see how it can be defined in a more formal way. A factored form is maximally factored if every sum of product, for every sum of product in that factored form, there are no two syntactically equivalent factors in the product. For every product of sums, there are no two syntactically equivalent factors in the sums. Okay, now we will rather than just going too much into technical depth of what does that mean, we will illustrate by examples. Okay, then again we will come back to this definition. For example, these two are not maximally factored. Now, why? Because trivially, because they are very trivial, because they contain trivially syntactic equivalent factors x1 in the sum and in their products and sum respectively. So, these are the sums and these are the products. Okay. So, you have a syntactically equivalent term over here. So that is what is being said. Every sum of products, there is no two syntactically equivalent factors in the products. For every product of sums, there is no two syntactically equivalent factors in the sums. That is what is being said. So in these products, so you can see there are two syntactically equivalent factors. Similarly, in the sums also it is there. So you can say that a sum or a SOP form is maximally factored if you do not find any kind of syntactically equivalent terms or factors in the sum of product, in the product terms or the sum terms. Okay. So obviously they can be factored in a very simple way. You can factor this one as x1 you can take as common and you will get x2 plus x3. So this is what is being gone. Okay, this one, this term, okay, this term can be factored into this one. So I mean first is obvious, the second one you can easily find out. You can just open this up and then finally you can find out that this is the most factored implementation. So first one is the product term, so you can just take the common one, and there is some term. So if you go out through these steps, you can find out that this can be represented in this way. Now this is the maximally factored form, because you can see that there is this is one product term and this you can consider one product term. Okay, so there is no any common, initially the x1 was the common syntactic factor, syntactically equivalent factor was x1, but there is no such a factor over here, and similarly in this case also there is no factor over here. So you can call these terms as maximally factored. Now obviously I mean they are going to, if you represent them, so they will be represented in what you can say minimum number of gates, they will be represented in minimum number of levels, as well as they will be taking the minimum number of fannies, that is minimum number of gates with minimum number of inputs. Okay, so this is what is the case. Okay. So now a few more definitions. So we say that the product of two cubes A and B is a cube. So there are two cubes like C1 and C2 say, product of two cubes A and B. So in this I mean C1 and C2 are A and B in this case. So if you take two cubes, because the standard we are using C1 and C2 for representing cubes. So simply, so if there are two cubes C1 and C2, in this definition they are terming as A and B. If you multiply them, so A dot B, that is C1 dot C2 is phi if there exists an x belongs to A union B and A prime also union X union B. That means what? Actually if if you say that it is x1 dot x2 and this one is say x1 prime, sorry, and this one is say C2 is say something like x1 prime into x2, something like this. So it is saying that there is an x which belongs to which is a term belonging to, is a literal belonging to C1 union C2, that is A union B, and also x prime belongs to this. So if you make a product, obviously x1 dot x1 prime, so it will be bringing it to phi, otherwise it will be simple A union. That is a very obvious thing. Okay. So AB is an algebraic product if A and B has disjoint variable sets, otherwise A and B is a Boolean product. Okay. So obviously if A and B has no terms in common, so if you make a product among them, so it will be a disjoint variable, so it will become a algebraic product, otherwise A dot B is it will be a Boolean product, because there will be some terms will be common and obviously one term will include other. So let us see by the example. So this one is an algebraic product because x1 plus x2, this one they do not have any common literal, or there is no common variable. So if you have so that is what, sorry, I am sorry, this is an intersection. Okay. So this is belonging to phi. Okay, and now this is an example of a Boolean product. Why? Because sorry, this will all be intersection. I am sorry. We are actually talking about this common. So these are all intersections. I am very sorry, because now if it had been the case, so x1, x2, x1 prime, x2 prime. So x is x. I mean, say in this case x1 is complement. So if you make a product of it, so x1 and x1 prime will cancel out, and c1 and c2 will be phi. But now if you have x1, x2, and in this case it is x1 and x3. Now if you make a product, so you will find out that it will be the common part will be only 1, and so you can have this thing like this. Okay. So this is about the idea. Okay, now in this case you see this intersection is phi, so this will be a Boolean, algebraic factorization. Now in this case, if it is x1, x2 and in this one, actually this one is the case, so it is a Boolean product because x1 plus x2 intersection, x3 is actually x2, because this is the common factor out of it, and so you are actually this is there, so they have a common syntactic variable, so it is a Boolean product. Okay, so this was the definition. Okay, now we are going for we are now actually coming from using those definitions. Now we are coming to the place, now we will try to factorize a given this thing. So now we are given function. So what do you mean by factorization? So say if you go to your junior school days, so if we say that you factorize 15, so we can say that 15 is equal to 5 into 3. Okay, or if we say that factorize 20, so you write is 10 into 2, or sometimes you write 5 into 4, so you are factorizing 20. That means given a, so say there is a high school fundamental, so the same thing is actually meant by factorization. So given SOP expression, expression f, so this is one SOP f, that is your main function which you have to factorize. So another d is there, so just take for the time being, say that d is the divisor. So you can find out, say that given an f, you want to factorize f, so some d is given to you, okay, that is the divisor. So you get a quotient and also you get a remainder. So but I mean this is very trivial, simple, like say 15 is equal to f considering high school days. Now some divisor is given to you, say d is equal to say 3, then quotient will be in this case will be equal to 5 and remainder will be in this case equal to 0. But now if I say the divisor is 4, then what do you say? Then the quotient will be 4 3 is 12 and 13 14 15 remainder will be equal to 2. So same thing is actually also holding for this functions. So what we are doing? So in this case division of an SOP is an operation where to SOP these things are generated this, okay, and this is your case. So f is the function which you have to factorize, some divisor is given. So how the divisor is given is the most difficult problem here, we will see how it is done, but given a divisor you can easily find out the quotient and the remainder. So what we are going, what we will be trying, what is the basic idea? So we will be given a function which you have to factorize. Now somewhere some d has to be given. So this is very important, the how d is selected. So as we will see that the most important problem in finding out the maximally factored for multiple level implementation, finding out the d is the most difficult problem. If somebody gives you a good divisor, for the time being just assume that somebody has given you a very good divisor, then what do you do? Now you divide f by d and you get a quotient and a remainder. Now you can try to see that can d be factored. So best idea is that I will give you a very good d. So assume that d cannot be free factored much. So you can factor q and r. So now again you have to factorize q and you have to factorize r. Again you require a good divisor and you have to keep on doing it, and finally you will find out that all the terms are factorized and you did not have to go for any more factorization in the maximally factored way. So now you can understand that selection of the d is very important at all stages. Okay, so that just we will see in this expression. So dq is algebraic product, the operation is algebraic, otherwise even if the product, this product dq is algebraic, then the division is algebraic, otherwise this is a Boolean product, and the operation is called Boolean division. So if r is 5, then d is a factor, otherwise d is a divisor. So that is very well known. If d can very well divide f, then the remainder will be 0. So in this case obviously d is a factor, otherwise d is a divisor, and this is the quotient. Okay. So now and obviously if dq is algebraic product, then the division is algebraic, and if the product is a Boolean product, then the division is a Boolean division. So that is division. So we already know that what is algebraic product, there is no little syntactic common terms in d and q, and if there is a common term in between d and q, then it becomes a Boolean stuff. Okay. So I mean as I told you, first you take some good d, then you do this, then again if you find that q and r can be again factorized, then again you find out another d prime for d and another d double prime say for r, and you keep on doing it. So every time you have to find out a very good d which can do it. So if you take a very poor quality of d, then then the factorization levels will be very slower, as we will see. Much more number of steps will be required to factorize it, and finally you may take a long time to find out a good factored forms, and also you may find out that you may not have received the most optimal factorization stuff, you are taking an improper d. So that is why selection of d is a very important factor, and I think in this lecture we will not going into elaboration and how do you find out a very good d, because it's a very well known, it's a very well upon when people are doing lot of work to find out how can you find out a very good d. So because the whole algorithm is standing on the feet of how to find out a good d. So once you find out a good d, then factorization is just a straightforward division algorithm which we can follow, which we will see, but selection of a good d is very important. Okay. So now given SOP of Boolean expression f, to convert it into maximally factored form, we need the following steps. Now we are assuming that somebody has given you a very good d, then how we have to go about the factorization. Okay, find a good divisor d. The exact and there are some exact algorithms as well as some heuristic algorithms. Actually, heuristics are not called algorithms, but I mean when you are just giving you, in a very formal computer science terms, there are algorithms and there are heuristics. We say in this way. So algorithms are generally exact algorithms. There is no point in heuristics over there, and heuristics are heuristics. But for the just for delivery sense and just for we are talking not going to that formal computer science. This is more or less a VLSI course. So sometimes with the slight abuse of notation, as you use of language, we are saying that exact algorithms and heuristic algorithms. But you know that for case of exact algorithms, there is predefined steps and there is no choice. This may always we are going to get the optimal solution. But in case of heuristics, we sometimes go about randomly searching the solution space, and sometimes we may not get the most optimal solution. But with size abuse of language, I mean for the CAD course, I mean I feel we can use these terms like exact algorithm and heuristic algorithms. Okay, so there are a lot of exact algorithms and heuristics to find out good D. So in this lecture we will just give you a very brief idea how it can be done. So once that is there, so you have to go for this, and then if you are selecting a very good D, then what is going to have? R is going to have as few cubes are there. That is, if I say that you factorize 15 or something like this, so it is a prime, let us take a prime number, say 13. So if I say that factorize it in such a way so that the remainder is as less as possible, so you can say that I will take 6 into 2, 6 is the divisor and the plus the remainder is 1. Rather than if I say that you take 5 as the divisor, so if I take 5 as the divisor, so it will be 5 into 2 and the remainder will be 3. So in this case, if you take a very good divisor, so R will have as less literal as possible. Okay. Now perform the division f by d to generate this. This step is simple, and we will see how the division can be done. Okay. So now we will see that the base also we will show you how this division can be done, and at the same time we will also show you that if you are taking a very good divisor, the number of times to go to the most factored form, maximally factored form will be less compared to if you are taking a bad quality divisor. So this is the say a function which you have to minimally factor, maximally factor, and this is the division x1 plus x2 dot x3. Okay. So now the process of determining D will be shown later, that is I told you how you can find a good D, we will see later, we will just give you the idea there. Okay. Then for each cube of D, now we will see how you divide. Okay. So D, each cube of D, in this case x1 and x2, x3, we look for cubes of F such that D has all the returns of F has all the returns of Di. So what do you do? Actually for D1 equal to x1, let us take the first term. Okay. Then we see that F1 is x1 dot x4, so you can represent it as D1 dot x4, right. So this one we are replacing by x1. Now x2 also has a F2 also has a x1, this is F2. So this is F1, this is F2, this is F3. So what we are going to do, for each cube in D, that is this is D1 and this is D2. Okay. For each cube in Di, we look for cubes of Fj such that Fj has all the returns of Di. That means Di actually becomes a subset equal to Fi. So if in this case you can factorize Fi by Di. So in this case x1 is common, so you can write D1 x4. Now in F2 is x1 dot x2 dot x3, so x1 is basically D1. So you can write D1 dot x2. So we write Vd1 as this one, that is if D1 is the term you are using. So D1 is the cube of the divisor you are using, so this D1, and we are writing x4 because first one you cut you get x4, and in the second this 2 and the second term x1 is common, so you get x2 and x3. Okay. So now this is done, and the last term if you see F3, and this one F3 is x2 dot x3 dot x4 and this is x1, so there is no common here, so we just cannot do anything with it. Now next term D2 is x2 dot x3, so we get you see x1 x4, so in the F1 you cannot do anything. In F2 if you see x2 x3 and this one is x2 x3, so you can easily represent it by x1 D2 because D2 is this one, so this is the case, and F3 you will also see that x2 dot x3 dot x4, so in this case it will be D2 dot x3. Okay. So Vd2 will be nothing but x1 and x4 because in this case this is x1 and in the final case it was what is D3 x3 x4 x2 dot x3, so yeah this is one is sorry this is x4. Okay. D2 is nothing but x2 dot x3, so this is x2 dot x3, so this is x4, so this is D2 is x3 dot x4. So this is a small typo, so this is D2 dot, it is not x3, it is D2 dot x4. So in this case we are having x1 and x3. So it may be noted that x4 multiplies both D1 and D2. So actually then you take a intersection of this, so you get x4. So you find out that x4 basically multiplies both the Vd1 and V2, so we can use factor this one x4. So x4 is a common factor for the whole thing, so you can write it in this way. So you write x4 is you just factorize into x4 is equal to x1 plus x2 dot x3, and x1 x2 x3 will be the remainder. So how you get x4? So what we have basically done, we have taken the first cube of D1 and find out the common terms. Okay, that is commonly factor. I have factored the terms in F which were possible. Then I have taken x2 dot x3. Similarly, I have done the same thing for f1 f2 dot f3. Then I found out that which is the common factor. So in this case I have found out that x4 is the literal which is common. So if we taking out x4, we find out this expression. So this one is becoming your remainder, this one is this x1 x2, this one was your divisor, and this one is your quotient. So this is the simple way I can actually go about factorizing a term or dividing a term. So for another example, same, let us take same f, and now D1 divisor is changed. So, it is now x1 and x2. So, for d1 equal to x1 we get x3 and x4, right, because if in this case if you get cut this x1 you get x3, and this x1 if you cut you will get x4 over here. So, these 3 terms there is no x1. So, Vd1 will be x3 x4. Similarly, if you consider this x2 term. So, in this case you will not get anything. So, in this case if you cut x2 you will get x3, in this case if you cut x2 will be x4 and this one. So, Vd2 will be x3 and x4, this x5 will be nowhere. So, in this case if we have Vd1 and Vd2, if you try to find out the common term, so you will find out that x3 and x4 both are common. Okay. So, in this case you can have a factor like x3 and x4 is the factor, because common thing is both over here, and you can find out that x1 x2 will be there, and this is the case. So, remainder in this case is x5. Okay. So, from the above discussion we may understand that once a good divisor is determined, the division procedure is very straightforward. You take a term from here, find out what are the common where you can actually have a factored form, where you can factorize, then you make Vd1. Similarly, you take the another term and repeat the same thing, you get Vd2, and you keep on doing it. Finally, you find out what is the common factor about this. If whatever the common factor will be, that can be used to factorize this term, and you can get a element. Okay, but if a good divisor is not used, then both R and Q can be factorized over here. So, you can see in this both the examples. So, in this case if you just have a look at it. So, it is x1, x2 dot x3 this one, and R1 is this one. So, you can find out that neither this Q, so this was a divisor, this one is Q, and this is R. Neither Q nor R here. Similarly, neither this was D, this was Q, neither R. So, neither Q or nor R can be factorized again, neither in this case. So, in this case you can say that this D and these divisors were very good divisors. Okay, but if you are not going to get a very good divisor, then what may happen? Then you may be again required to factorize Q and R. Okay. So, in this case if this is not a good divisor, then Q and R can be factorized again, they may not be minimum Q. So, again you have to do this. In such a case Q and R to be factorized again, and the process is repeated till no more factorization can be done. A typical algorithm is given below. So, it is very simple, you take a division. Okay. So, this is what is the thing. So, if F cannot be factored, you return F, that is the minimally already you have done. So, this is the factorization algorithm. You take an F, you take a division, you divide. Okay. That is what is the idea. Now, D is the divisor F. So, you have to find out a good divisor, that is very important. So, it is based on heuristic or exact algorithms. So, that we are going to just discuss. There are some of the references you can find out in the handouts in the lectures. So, some handouts I will be giving, we will upload it with these lectures. So, that you can find out some good algorithms which can find out how a good divisor can be obtained. But anyway, it is a very complex procedure. So, we are not discussing in this lecture. Okay, but you just give an idea how you can find out some heuristics which can determine a good divisor. Okay, so now you find out a good divisor. Now what you do? You do this division as given these two examples before. So if your divisor is good, you will find out that this remainder and the quotient they cannot be again refactored. But if this is not the case, then what you have to do? Again you have to factorize R. Again you have to factorize Q. And in fact, if you have not taken a very good divisor also, then again you can be able to factorize D, and the processor will keep on doing it. But for the general cases, D need not be factorized over again, but it may happen that Q and R have to be factorized. But in the worst case, if you are not a very good person at selecting D, then you can even use a D which can be again refactored. So again you keep on refactoring D, Q and F till you reach a time where this expression cannot be refactored again, and you return the values. Okay. So that is what I told you is given in this minute divisor. So you start with divisor is to find a good candidate. So then you actually divide this, then you can generate this one. So if you can again factorize Q and R, you keep on doing it till you cannot be again factorized again. So that is the idea. Okay, now we will be illustrating the whole things using some examples. Okay, so this will be the F, okay, and then let this be the D. Okay. Then if you repeat all these steps, you will find out that this is the quotient and this is the remainder. So in these examples I am not going to again show how it comes, because you can very easily find out. You can very easily find out the same procedure. First you take x3 and find out the terms, then you take x4 and you find Vd2. Okay, then you find out what the common terms. Then you actually in this case x3 plus x4 you will find out. In this case if you do it, you will find that x1 and x2 are the common terms over here. Then so it will, your expression will be x1 dot x2. dots is this one plus 4, and these terms like x1 x5 x1 x6 and x7 x cannot be included, they cannot be factored by using this division. Okay, so this is your quotient and this is your remainder. Okay, in this case we consider this one, the division is this, so this is the remainder. Okay, and the quotient is x1 and x2. We note that quotient cannot be factorized again, this is obvious, but r can be factorized. So in this case you can see that, you can say that this may not be a very good division. So this is not a very good division, because using this division what happened, this quotient you have got and this remainder you have got, quotients cannot be factored, that is one good point, but the bad point is that remainder can be again factorized. It can be easily factorized, but if you take this x1 out, so you take x1 out and this can be done. So finally we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have 8 literals and we reach in 2 steps, because first you get this term and then again you have to factorize r. So time step required was equal to 2 times, and number of literals is equal to how much? 1, 2, 3, 4, 5, 6, 7. Sorry, 1, 2, 3, 4, 5, 6, 7, 8. So 8 literals from this. So this is what I have obtained. Okay, now you see same f, but now we have changed the factor. Okay, so we are just trying to show you that how important d is to get a maximally factored form. Okay, so now d is this. So now if you take x1, so you can easily find out that this one will be your quotient, okay, by the same term, and remainder will be x4, because you see x1 is common over here. Every time you can cut it off. So this one will be your quotient and x7 will be remaining, so this is remaining. So this one is your quotient, this one is your d, and this one is remainder. So it is very obvious that remainder cannot be factored. D is a good resource, d which cannot be factored, but you can see q can be further factored. Okay, so if you further factorize q, you can find out that this one is the answer. So in this case, how much? 1, 2, 3, 4, 5, 6, 7. So you have 7 literals, and the time literals is equal to 7 and time step equal to 2. So if you consider this d, time step is 2 and literal is 8. So in this case time step is 2, time remains same, but we have decreased 1 literal. So you can say that d equal to x1 is a better divisor compared to x1, x3 plus x4. So there can be even further better divisors, as we will see, but what we are going to see is that based on the divisor, what is the idea? Based on the divisor, the time taken to factorize the function also changes and the quality of solution also changes. Now we take another example with now d equal to 2. So if you take d equal to 2, you will find out, if you do that, you will find out the quotient is this and remainder is this. So in this case, you can find out that after the division, this one is the quotient, and we may note that q can be factorized at this one and r can also be factorized at this one. So now with this division, what happened is, now you have to factorize, you have reached a situation, so q can also be factored and r can also be factored. So in this case, what happened? Q could not be factored, sorry, in this case r could not be factored, but q could be factored, and in the first stage what happened? Q could not be factored, but r could be factored. So you see, depending upon this choice of remainder, what is happening is, sorry, so depending on the choice of this divisor, so what is happening, the different types of situations are arising. Both q and r can be factored, r can be factored, q can be factored, and so forth. Okay, so if it x2, so this is the quotient and this is the divisor. In this case, both of them can be factored. So now the solution is this one. So this is the final solution. So in this case, you have 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 literals and again 2 time steps. So 8 literals and time step is also equal to 2. So you can say that 2 is a bad, what you can say, not a good factor, not divisor again, but 2 is a worse divisor than x3 plus x4, because in x3 plus x4 you require 2 time step and literal is 8. So in this case also it is the same, 8 literals and 2 things, but here after first step you have to factorize both q and r again. But if you take x3 plus x4, then time and literals are almost same, but actually in the second step we are factoring only r, we are not factoring q. So you can say that the best divisor among the 3 is this one. So where we have 7 literals, 2 time steps, okay, and you need to factorize only the q. In this, the second one is x3 plus x4, where the literal is 8, time is 2, but you are factoring only r. And the worst one is x2, okay, where you have, you have again time step is 2, but you have to again factorize q and r both, and again the number of literals uses 8. Okay, so this one is the most bad, the worst among the 3 divisors. Okay, so let us take another example. So we are just showing 2 different examples that how d is a very good quality, and how d controls the quality of the algorithm or the flow of multi-level implementation. Okay, so this is another f, and they have taken a factor, the divisor called d. Okay, so in this case, if you take this as d, you will find out that this is your quotient, remainder is 0. So you are getting something like this. In this case we can call that here D is nothing but D is a factor, because this can very well because it can factorize F without generating an R remainder. Okay. So, this one is the case. So, you may know that now we can here actually this is your quotient, you can be further factorized into this. So, the maximally factored form you can find out for this one will be x3 plus x4, then this guy, this is your this part actually is actually your Q. So, you can factorize this into this. So, when we take this one, you get a maximally factored form in 2 steps having 6 literals. So, in this case is 1, 2, 3, 4, 5 and 6 literals are there. Okay. So, that is what is being said. So, this was another example where you can say that this is a type of divisor. Now, if you want to find out whether it is a good divisor or bad divisor, so you can think that this is a very good divisor, because at least you could generate R which is remainder is 0. So, if you could remainder generate as a 0, that is a very good divisor you have found out. Basically, you can fully factorize an expression, remainder remaining is 0, that means there is no cubes over here. So, you have made a lot of saving in the implementation. Now, you can again find out that you can be again refactor, that is a different story. So, if you can find out a divisor which can entirely divide a function without remaining a generator, then you can say that a very good divisor, because what? Because you are not generating a remainder, that means your number of cubes have reduced, so your implementation is towards the minimal. But just like prime numbers, you cannot, there is no divisor which can divide the number accepting the number itself. So, obviously, if this is F, you cannot generate this is equal to 2, this is equal to D. That is a very foolish way of thinking about it. So, just like some prime numbers are there which cannot be further factorized without 1 and the number itself. Similarly, there can be some functions for you can never find out a divisor where the remainder will be 0 excepting the function itself. But with that cannot be obviously use the divisor over here, which is very well known. So, if some functions are there for you can find out a divisor which can actually give you the the minimum representation, remainder is 0, then you can consider it as a very good division. Okay. Now, you see, so this one was what? It was 6 literals, okay, in this case. Now, in this case, now if you take same F, but now you consider x1 plus x2 as a divisor. So, you will find out that this is the quotient and this is the remainder. Okay. So, now you see that x1 plus x2 is not a factor, okay, but in this case x3 plus x4 was a factor. So, what happens now in this case? This is the quotient and this is the remainder. So, if you represent F, so you are going to get something like this. So, in this case you can find out that both R and Q can be further factorized, and finally you will get this as the solution. Okay. In this case D is the divisor. So, you have maximum factored form is having 8 literals and time step is 2. So, it is 1, 2, 3, 4, 5, 6, 7, 8. So, 8 literals and time step is 2. In this case the number of literals is 6. Okay, 1, 2, 3, 4, 5, 6. So, that is why if you find out a divisor actually which can generate a remainder equal to 0, then you can consider that is a very good kind of a divisor. So, now we have seen that once you can find out a very good divisor, then the problem is very simple. So, what you have to do, that is this algorithm steps we have already seen, that is the steps we have seen, that what you do, you just generate the cubes over here, you generate the cubes over here, you factorize each of the cubes by D1, then by D2, then by 3, and then find out the common factors, common literals, and then you generate the quotient and the remainder. Again you have to try to find out whether the quotient and the remainder can be factored, and you keep on doing it till you reach a stage where nothing can be factorized over again. So, that is what is going to tell you that we have gone for the most factorized term. But the most difficult problem here is that how can you, given a function, how can you find out a good divisor. So, that is a very difficult problem, and we are not going to elaborate in this, but rather we can say that there are a lot of exact algorithms, there are a lot of heuristics for this which you can find out if you are interested, you can find out in the references given in the handouts that you can read. But you can find out that why it is very complex, because if you see that for the 2-level implementation there was some solution space. Okay, the solution space is what? Is a subset of the primes. Okay, that is a solution space. But in this case you are starting with the subset of primes, because you have to go for a minimal level SOP of minimized form, that is a subset of primes, and from there you have to find out that you go for a multi-level factored form, that is that. Again, I am not going into elaborate, but just you can think of that. If subset sum, that is you are given some 10 prime implicants, you have to find out a subset of them, that is 2 to the power number of prime implicants, that is the solution space. But in this case, you can see depending on different type of factors, okay, you can see that the different type of representation that are coming up. So, you can just generalize and think how big will be the solution space. The solution space in case of multi-level implementation is much larger than the 2-level implementation. 2-level implementation is nothing but the power set of the prime implicants. But in this case what is happening, it is given a different type of factors, so factors can be n. I mean there are n number of different ways you can generate a factors, and for each of the factors you can find out, you have just seen how different your factorization procedure evolves. So you can think of the solution space is extremely large compared to 2-level implementation. So that is why the algorithms or the heuristics to find out a good divisor is also a very difficult problem. So whenever the solution space is small, then your algorithms are simple. Whenever the solution space is very high, the algorithms are complex. That is why finding out a good divisor is a very difficult problem, and we are not going to elaborate in this lecture. But we can think a very simple heuristic can be, a divisor is a single cube. You can think that I will always take divisor as single cubes rather than x plus y or something like that, and involves littles that occurs in most cubes of f. So just go for this. So if I just give you an example, I want to find out a divisor of this one. So I will not take any divisor like x1 plus x2 or something like that. I will take this either x1 or x2 or some up to x6, any one of them. Now which I will take? I will take the literal which is common to most of that. Like in this case 1, 2, so x1 is in 2 places, x3 is in 1, 2, 3, x3 is in 3 different places, okay. x5 is in 1, 2, 3, 4, x5 is in 5 cubes, okay, and similarly x6 is in 1. So you can say that I will take x5 as a divisor, because x5 is appearing over here, appearing over here, appearing over here, appearing over here. So if I take that x5, then I am going to get as x1 plus x3, sorry, x1 x3, okay, I will get x1 x3 plus x1 x4 x2 x3 x2 x4 and so forth. So that is, if I take the literal which is common in most of the cubes, then I can be able to reduce, factorize the expression f in a most better way. So this is one very simple heuristic you can think, but exact algorithms and better heuristics are more complex, okay. So with this we are actually closing this this discussion, and we are coming to question answer session. Okay, so we just say that, give an example to show that Boolean division procedures better solution to algebraic division. That is very important. And now, till now in the discussion what we have found out, we have discussed that all we have done is basically nothing but we are all talking about different type of expression, divisions, etc. are all algebraic division. So what was the idea of algebraic division? That is, if you have two terms, we should not have some same term x1 here and x1 in this. That is the idea. But if you allow this, then it will become a Boolean division. And in fact, Boolean division will give you better solution than algebraic division. But Boolean division is more complex than algebraic division. That is why we have not gone into this. But just to give you the idea that what is the case. So if this is your some f, okay, then there are 3 equivalent factored forms. Okay, first one is having 12 literals, the second one is having 11 literals, and the third one is having 8 literals. So this is the first, this is the second, and this is the. So you can observe that these two are algebraic, okay, and the third one is a Boolean, because you can see x1 and x1 is common over here. So this is a very complex topic, and we are not going into details in this course, but the idea is that you can easily you can verify if you go into depth that Boolean expression, Boolean factored form are further minimized compared to algebraic form, okay, but algebraic division and algebraic minimization of the factorization is a more complex procedure, so we have not gone into depth of this. That is why we are just giving you an overview, and in fact multi-level implementation is a very complex topic. So in this course we have tried to give you the exposure in a very minimal way, just to give you an idea that given a 2-level form what is the problem and how we can go and approach in a multiple level implementation. We have not gone into any amount of depth by any means in this multi-level implementation. So there are lots of work which has been done, and a lot of work still going on in multi-level implementation, because that is what is practically required for implementation. So this was just the tip of the iceberg for multi-level implementation we have given you. In the end, so we have also shown that algebraic factorization, if you compare with Boolean gives a much better solution, but again these are very more complex stuff, and we have not even discussed how to do Boolean level factorization in that case. Okay, so with this we close this lecture, and also we come to the end of the design module. So in the design module what we have seen that we start off with design specification, and from design specification we go for high level synthesis. From high level synthesis if we go for Boolean synthesis, first we go for first we go for 2-level implementation, and if it is a sequential circuit then we have to go for state minimization and state encoding, and then we go for use minimization, and if it is a combinational circuit we can directly go for 2-level minimization, and after the 2-level minimization is done we go for multiple level implementation, and the final netlist or the gate level implementation goes on for what you can say, fabrication. But before we go on for fabrication, we have to see that all the transformation we have done, specification to high level design to Boolean level design, 2 level, from 2 level to multiple level, that they should be all equivalent. That is, there should not be any change in specification in between this stuff. So in the next module, we are going to see formal verification techniques that will assure that design A is equivalent to design B is equivalent to design C. So you can say that when the final design is out, you can claim that my final design which I am sending for fabrication is equivalent to my specification, or they meets my specification. So in the next module of the course, that is, this course is on design verification and test. So in the next module we will see about verification. Thank you.